Today we're going to be talking about the odd juggler problem. Now you might think to yourself, I've met some jugglers before. They were all odd. So what do you mean by the odd juggler? Well, here when we talk about the odd juggler, we're talking about restricting the type of patterns that they can make. And in particular, we want to say the only types of throws they can make are odd. Now, if you think about how we're describing throws, remember that the throws count the beat. So there's like a 1 is a quick throw across, a 2 up and down, a 3 is across, a 4 really high up and down, 5 really far across, and so forth and so on. So in particular, the odd throws switch hands, the even throws stay in the same hand. So odds go across, evens stay in the same hand. So another way to think about the odd juggler problem is one where it says, look, whenever I have a ball, I'll always throw it to my other hand. Okay, well, there's a natural question. If we want to make sure that all our throws are odd, how many such patterns are there? And we're going to discover that the answer is kind of interesting in that there's a couple of different possibilities that emerge. So let's start with probably the simplest case. Well, what is that? Well, let's suppose that our period is an odd number and the number of balls that we want to juggle is an even number. Okay, what happens there? Now, at first it sounds like, there's going to be a lot of work here. But let's think about one of our patterns. So suppose we have such a pattern. Let's just grab one for a second here. So our pattern we'll say is, T1, T2, all the way up to Tn. Okay, and now we have one of our most basic facts. It was the one that we use strings to prove, which says we can say something about the throws. And in particular, we can say, hey, if you add up all these throws, what must be true? Well, what must be true is that it's the period, which is n, times the number of balls, which is p. All right, so far, all right. What does that do for us? Well, let's look at parity, which is really another way of saying things being even and odd. Parity is a wonderful argument. It turns out to be amazingly useful, much more so than you think it should be, given how simple it is. So let's look at the right-hand side. That's, I think, the easiest of the two sides. I know that n is odd, and I know that b is even. If I take an odd number times an even number, it has to be an even number. All right, well, great. Now let's turn to the left-hand side. Well, here there's a bunch of terms, but let's keep track. Each term, by our assumption, is an odd number because that's our goal. We want all our throws to be odd. So each one of these is an odd. How many are there? Well, an odd number of them. So if you add up an odd number of odd numbers, sounds a little bit odd, what do you end up with? Yes, you end up with an odd number still. So this other side, left-hand side, when we add it up, has to be odd. And now we come to our dangerous, wait a second, something's not right. Because something's not right. In particular, what we have is the situation says, look, this odd thing has to equal this even thing. But an odd number can't be an even number. So they can't be equal. So what's our conclusion? Well, our conclusion is we couldn't grab a pattern. There are none. And so, in the case when n is odd and b is even, the answer is 0. No such patterns exist. Wow, nice, clean. Hopefully all the cases are going to be this easy. Well, no. But each one is interesting in its own way. All right, good. So now let's go to our next case. So in our next case, we're going to have both n and b. So our period and number of balls are going to be odd. What about that? Well, we'll already write down the answer, and then we'll try to figure out, well, why is that the answer? So the claim is that it's b plus 1 over 2 to the n, minus b minus 1 over 2 to the n. Okay, now you might say, wow, that feels really familiar. Well, it should. It's not just any random formula. In fact, this is the formula for the number of patterns with exactly b minus 1 over 2 balls, but no other restrictions. Okay, so how do we get there? Well, what we can do is we can say, look, for everything that we want to count, and the things that we want to count, we want our n and b to be odd. We say, look, over here, I have a pattern, same period n, with b minus 1 over 2 balls, but no restriction. So if I can say, hey, there's this nice pairing, then to count the original thing is the same as to count this new. And it's something that we've counted before. So the trick here is just to say, well, why does it work? So what can we do? Well, suppose that we have a pattern that works nicely. And what are we going to do? Well, we want to somehow manipulate it. So let's start with something that actually is an example. So suppose we look at the pattern 5, 3, 1. All right, that's something that can be juggled. Not so hard to check. And notice n is odd. It's period 3, so n equals 3. And how about the number of balls? Well, it's got to be odd, but it turns out it's a 3-ball pattern. All right, so 5, 3, 1. Well, here's sort of our thought process. We look at ways that we can manipulate our sum. We can manipulate our pattern. So what we'll do is we'll say, okay, step 1 is we'll subtract 1 from every throw. And the good thing is, because they're all odd, I don't have to end up with a negative, because I don't have 0. So I know I'm not going to end up with a negative. And because I'm doing it to each throw, it's going to maintain being a pattern. See, I can always add 1 to all the throws or subtract 1 from all the throws, and I'm good to go. So in this case, we get down to 4, 2, and 0. All right, now we have a pattern 4, 2, 0. Okay, now what? Well, we want to divide by 2. And you say, okay, well, how hard could that be? And so step 1, I should have made some notes here, minus 1 from each throw. And step 2, well, we want to divide by 2. Now, you have to be really careful here. You notice that we're putting some quotes here, divide by 2. And why are we putting our quote marks here? Well, if we just take it literally, we'd run into some problems. In particular, if you take 4, 2, 0 and divide all the throws by 2, well, what would happen? You'd end up with 2, 1, 0. And this is not a pattern. So, trouble. But there is good news for us. It turns out that you don't just divide each throw by 2. It's really a combination of divide the throws by 2 plus do some rearranging. Now, how to rearrange, that's sort of the thing that you have to be careful about. And so, well, how does it work? And the answer is the following. Well, I'll write it in general, and then we'll go back and do the specific case. So suppose we have our pattern T1, T2, all the way up to Tn. And remember here, n is an odd number. And now, what do we do? Well, and each one of these throws, by the way, is an even number. So what we do is we rearrange in the following. We're going to take T2 over 2 as the first one, then T4 over 2 as the second one, and T6 over 2 as the next one, and so forth and so on. So, in other words, we're going to take every other one. So, how does that translate here? So in our case, we would have what? Well, here's our T1, T2, T3. So we'd say, okay, T2 over 2 would be what? Well, it'd be 1. I can take 2 divided by 2. I'm pretty good at that. Now you might say that, well, there's no T4, wrap around. So T4 is the same as T1 in this case when n equals 3. Divide by 2. 4 divided by 2 is 2. T6 is 0. Divided by 2 is 0. And this is a pattern. And it's not just a coincidence that it happened to work. Indeed, it's 100% guaranteed to always work. Now, why is it always guaranteed to work? That comes down to some modular arithmetic and some gentle bookkeeping. Basically, what happens is we're taking advantage of the fact that n is an odd number. And in particular, we know that 2 is relatively prime to n. That's the key of this argument. Because 2 is relatively prime to n, that allows us to say, oh, in terms of modular numbers, 2 has an inverse. And so because of that inversion that happens, that says, look, if everything was distinct, and then you carry out this rearrangement, it's still distinct and still satisfies all the modular constraints for being a pattern. And there's some notes about this from an earlier homework assignment you can take a look at. I don't want to go too much into this because the real fun stuff is to come. All right, now that you sort of say, okay, here's this process, we can relate a pattern that we want to count with a pattern that we know how to count. Let's keep track of how many balls that went along the way here. So initially, if this first pattern had b balls, then after the first step, well, if you subtract 1 from each throw, it's b minus 1. And now if you divide each throw by 2, well, what happens is you're going to divide the total number of balls by 2. Why? Well, we go back to the number of balls times the period is the sum of the throws. So if we divide each throw by 2, then we divide that sum by 2. Well, we haven't changed the period, so it must be the case that we divide the number of balls by 2. So we have this nice pairing. Now, same idea, you can go the other direction. Multiply everything by 2 with a proper rearrangement and add 1. So everything works out to go back and forth. All right, so that's that problem. Great. So we've now handled the n is odd. We've seen if b is even, 0. If b is odd, we related it to something that we already solved. That leaves the even case. So let's turn to that. So the even case is, I think, the most interesting because it's sort of like, oh, well, first off, we don't have to separate balls being even or odd. And it gets kind of like, it's a mystery. How does this all fit together? So let's think about it in terms of building up from our minimal juggling patterns. I'd like to think that whenever you talk about problems where you say, let's put some restrictions on the types of throws that we can do, the best approach is to say, can we go back to minimal juggling patterns and put restrictions on how to build up? A lot of problems can be phrased that way, and I think that's why this is a fairly good approach to take. So here we go. We have n is even. In this case, we'll go through n equals 6. We have our board. Now, where can we put a rook? Be careful here. Can we put rooks anywhere? Now you might say, well, we can't put a rook on a 2, right? For example, because that's even. But remember, we are allowed to bump up. Will always be even. And now we're taking advantage of the fact, well, if n is even, if I start with an even number and I add an even number on top of it, it's still even. So no matter how I bump it up, it will always be even. So I could never put my rook on top of an even number. Can I put my rook safely on top of an odd number? Well, I have an odd number, and when I add the period to it, no matter how many times I add a period, an odd plus even plus even plus even plus even is still odd at the end. So I can put my rooks on odds, no problems at all, no restrictions. I can do whatever I want. So we say, oh, so what's happening is really we're going to throw out half the board. In particular, we can say, look, we have to put our rooks down where we only have odd numbers. All right, so let's cross out our even numbers. So we'll go through really quickly and cross out all of our even numbers. Now, what we'll see is we kind of have almost like a checkerboard pattern starting to emerge here. And what can we say? Well, all right, it might feel like this seems more challenging than where we just were a few minutes ago. How do we handle this? And here's sort of the key insight, is look at the board that's left and don't think of it as one board. Think of it as two, in particular, two small boards. So I'm going to highlight one of them. And so in particular, I'll use some purple here. And what you'll notice is that there's sort of now three things going on here. There's the dark green, which has been knocked out, won't be considered, can't put any rook there. There's the purple, and then there's the remaining white ones. What's true? Well, what's true is that if you look at the purple, it's really a 3x3 board that's kind of been stretched a little bit. In that it's a 3x3 board that has been stretched a little bit. And similar, the white is, again, it's a 3x3 board, it's just been stretched a little bit. So we can say, it's like we're putting rooks on two smaller boards. In this case, what would our boards look like? Well, one of them would be, if we do the purple one, 1, 3, 5, 5, 1, 3, 3, 5, 1. And here, our other board, and this is coming from the white one, which would be 5, 1, 3, 3, 5, 1, 1, 3, 5. So now we say, okay, in some sense what we've done is transform the problem. Instead of putting rooks on a large board, we're going to put rooks on two small boards. So the good news is we know how to put rooks on a small board. We just have to sort of keep track of our count and how to go back and forth. Once we have that, life is good. We've got our answer. So let's think about what's going on. Here's where things get interesting. Well, things are always interesting, right? Of course they are. How to think about this? Let's think about what we can say. Now, there's a little bit of subtlety here. And the reason there's a little bit of subtlety is we're not going to be able to translate exactly like we were before, but almost. And I want to mark where things are below the diagonal of the big board. So if we turn to our purple board, well, the part below the diagonal still feels like below the diagonal. But if we go onto our white board, the part below the diagonal, it's actually going to be the part that's on or below the diagonal in that small board. That's why, okay, there's a little bit of a twist. But let's see what happens. Now, what we're going to do is we're going to add. And so there's going to be a sum. This is actually a double sum, but to save notation, we put both indices underneath. So we're going to add up over all choices of I and k. As with any sum, it's important to understand what are things representing. So what k is the number of rooks below the diagonal on the big board, right? Not the small boards, the big board. So that's, in the past, when there was no other restriction, okay, whether you number nk, life is good, woohoo, and we were happy. Now it's a little bit more interesting here. Now, why? Well, because we've sort of broken it apart below the diagonal into these two smaller pieces. And so we know that there are k rooks to be placed, but we could place, all of them in one or all in the other or some combination of the two. And it's this balancing act that says, well, how do we do that? And so that's where the I comes in. And so what would the I represent? Well, I is going to be the number of rooks below diagonal on the small, and for lack of a better word, what's currently colored purple board. Okay? So the number of rooks down here. Okay, now that we have what we're adding over, what do our indices represent, let's see if we can sort of figure out where all our terms are coming from. Let's go one term at a time. So we want to put I rooks below the diagonal on the small purple board, right? Well, that's saying, number of rooks down here. Okay, no problem, no problem. And that's just the Eulerian number. We know the size of the board is n over 2. We want I rooks below. All right, nothing too surprising. Now, what goes on? Well, if we know that there are I rooks that go into that, what we can do is now go to the other board and say, hey, other board, how you doing? And but more particularly, say, look, there has to be k minus I rooks in that diagonal or below. Remember, we need to have a total of k rooks showing up in these two pieces to get our right count for the number of rooks that are going to be below the diagonal on the big board. Now, the bad news is, well, that's not the right shape. The good news is, say, hey, hold on a second. Look what's lurking up above. This is the right shape. So, in particular, we can say, oh, hey, if there's k minus I rooks down here, there's a total of n over 2 rooks on the board. That must mean that there's n over 2 minus, and we'll put parentheses here, k minus I rooks that sit up here. So what we can do is we can actually count the number of ways to put n over 2 minus k minus I rooks in this slot right there, which puts the right number of rooks in the part we need. So that's where we get our next term. So place rooks on the purple board, place rooks on the white board. And now we've put our rooks. We'll have a total of k rooks, which will correspond to k rooks below the diagonal on the big board. And again, as I varies, we capture everything. Now, what's left? Well, the last part is to say, we know we have k rooks below the board on the big diagonal. That means we have k balls already spoken for in the pattern. We want to get to b balls total, so we'll need to sort of do some bumping up. In particular, the number of times that we'll need to bump up will be b minus k, right? K plus b minus k gets us up to b. So we're going to do, this is bars and stars type arguments. So this is going to be our bump up to b balls. All right. Now, here, what do we have? How many slots are we going to go into? And this is a little bit different than what we did before. See, previously we said, oh, less than b plus 1. No, we want exactly b. So in this case, well, we think of there being n rooks, right? That gives us our n bins that we put things into. So it's the number of balls. Well, okay, I'm thinking balls and bins. But bars and stars. So here, stars, that's b minus k. And here's your number of bars, n minus 1, because we're going to split things into n groups. And so, of course, choose n minus 1. So this part right here gets us all the way up to b balls. So place rooks on the on the two small boards, fantastic. And then say, okay, how much you need to bump up, how many ways to do that, and that gets us our total count. All right, we've got a formula, and in some sense, it is the right answer. But we could probably make it look a little bit nicer. So let's work a little bit. And you might say, well, if it's right, why bother? Well, there's something about beauty and math, and it's not. Sometimes if we say, look, it's the right answer, and don't say, well, can it simplify, we miss out on the beauty. We don't want to do that. That sounds terrible. So let's enjoy the trip. Let's take a look at some of this beautiful stuff that's about to happen. All right, here we go. We're going to do some manipulation here. So nothing too surprising here. Indeed, we're only going to use two tools to help us simplify. But it's still good to sort of practice going through it step by step. So let's begin. So we have our initial sum that we just talked about, and now we look for certain things to simplify. Generally speaking, the goal in simplifying is to make the expression look easier. And things that we can do are exploit properties of the numbers we're looking at. In this case, we're looking at Eulerian numbers and binomial coefficients. And then we can also think about reindexing. Reindexing is just a fancy way of saying, give things a simpler name. Now, in our case, see we have this n over 2 minus. We know something about the Eulerian numbers. They're symmetric, which means that if you read it one way, you get the same thing as if you read it another way. So we can exploit the symmetry and say, oh, well, this Eulerian number is the same as the Eulerian number where we, instead of n over 2 minus k minus I, it's n over 2 k minus I minus 1. So that's the first step, using symmetry of the Eulerian numbers. All right, so far, so good. Okay, what's the next step? Well, we say this is kind of a weird looking thing, k minus I minus 1. Oh, let's give it another name. And we can. So what we'll do is we'll call it j. So what are we going to do? Well, everywhere where we see a k minus I minus 1, we'll replace it by j. Now you might say, well, what are we really doing here? What we're actually doing is we're replacing what used to be our variable k. We're going to replace it by j. Now you might say, why not I? Well, I is already there and we're not going to change. So secretly, since we're starting with this relationship, this k minus I minus 1 equals j is the same as saying k is going to be equal to I plus j plus 1. So that's what we're going to do. Everywhere we see a k, replace it by I plus j plus 1. Now, since we're summing over all possible choices of I and k, after we do this substitution, after we change this name, we're still summing over all possible choices, but now with I and j. All right, so this becomes a really nice, simple Eulerian coefficient, n over 2j. All right, and here, you need to do a little bit of work, but remember the k became I plus j plus 1. So we end up, this minus k, we subtract I, subtract j, and subtract 1. We already had a minus 1. That's why you end up with a minus 2. All right, what's the next thing we're going to do? Well, in some sense, I already think this is really beautiful, but this is getting kind of messy up here. So this next one is a little bit of magic in some sense, and it's not the most obvious thing to try at first. I know because it took me a while to think about it. But one thing we can do, there's always a good adage. I remember I learned this a long time ago by a very, very smart, very kind professor, and said, look, if you want to solve something, very simple procedure. The first thing is try something. And then next, if it doesn't work, try something else. But never give up. So there's always this thing of saying, hey, try things. It doesn't hurt to experiment. Yes, you might hit a roadblock and have to go back, or you might not. It's wonderful to say, what would happen if? And explore what happens. All right, so back to our regularly scheduled problem. Well, so we're going to use symmetry on our Eulerian coefficients. And what happens? Well, n over 2I by symmetry becomes n over 2 minus I minus 1. The Eulerian numbers has that sort of minus 1 floating around. Sometimes it can throw you off because of the symmetry. Same idea. This n over 2j, n over 2 minus j minus 1. All right, so we have our Eulerian numbers symmetry. Now, how does that help us? Well, notice we can take this expression, minus I minus j plus n minus 2, and rewrite it as n over 2 minus I minus 1 and n over 2 minus j minus 1. See that two n over 2's combine together to give n. There's a minus I, there's a minus j, and a minus 1 makes minus 2. And these pieces match. Oh, it's like it was meant to happen. I hope it was. It's too good not to have been meant to happen. So let's reindex. Okay, so we're going to change this n over 2 minus I minus 1, we'll call it S. N over 2 minus j minus 1, we'll call it T. Good. So there's an S, there's a T, there's S, there's T. So our sum is really now all S and T, and it's n over 2 S, the Eulerian number, n over 2 T, the Eulerian number, and then binomial coefficient B plus S plus T and minus 1. And that is as simple as I can get it. As far as I know, there's no simple expression for this formula, which, that's fine. A lot of math, you get this happening, where you reach a point and be like, aha, and then, well, we don't know, because we don't. There's a lot that we still don't know, and that's okay. That's all right. One reason why I do like this formula is there's something interesting that's going on. So in particular, if we take a look, we can say, hey, let's go back to what we did before, where we said, suppose we just want to have period end b balls, no restrictions. How can we rewrite it? Now we got down to this really cool thing like, b plus 1 to the n minus b to the n. But if we hadn't been able to do that final step using Warpitsky's, one of the ways it could have been written is as the sum over s of ns, this Eulerian number, b plus s, and minus 1. And I just love how similar these two expressions are. And, what's the big difference? Well, here, it's sort of like you're splitting it. You have two sums instead of one, s and t, and you split the n to n over 2, and here you have s and t. And it just feels right, feels beautiful. What a glorious, happy answer that we've gotten. Now, at this point, you might say, all right, fantastic. So suppose you wanted to look at the even juggler. Could we do that? And the answer is, well, we're basically done. Why? Well, if I want to solve the even juggler problem, I can say, well, first add a 1 to all the throws, and now you're in the odd juggler problem. So they're really the same problem. But there's another thing you could do. So another thing you could do is say, well, suppose I were a three-handed juggler. Now, it's very unlikely. If you're a three-handed juggler, the fact that you juggle is probably not the most interesting thing about you. But, if you look back at a lot of the math, all right, the math makes sense. We can handle being a three-handed juggler. Because implicitly, left and right, you haven't really played a role in terms of the patterns, in terms of the counting. Okay, so we're a three-handed juggler, and let's just say, look, I never throw a ball to the same hand. What does that mean? Well, it says I don't want to have any throw that's a multiple of 3. What do we do then? And the answer is, I don't know. All bets are off. Yeah, there are things that we still don't really have a great way to do it. Now, there's always small cases we can handle, but something systematic, we got to think about that. Well, It's good to have problems. More problems for us to think about, more problems for us to work on. Hey guys, just a little quick side note. Some people see problems and like, oh, there must be a nice answer. Let me just get my hands on it. And I would love it if you find a nice way to simplify that sum, that, for the odd juggler problem, so that it has, it simplifies down to this beautiful, clean answer. Please, I want to know. So to help you get started, if you're interested, I generated some data. Of course, you have the formula, you can generate it yourself, but sometimes their Illyrian numbers are not so easy to find. In many cases, they're not automatically programmed in. And so here's the data for some small cases of B and N. And, there's a lot of them, right? But, lots of possibilities. So keep looking, keep finding. And if you see anything beautiful, let me know. All right.